Okay, please have a seat. So we're very fortunate to have Brice Ménard here today to give our colloquium. Brice did his PhD at the Max Planck Institute for Astrophysics in Garching and at the IAP in Paris, where he mostly focused on weak lensing studies, but also became interested in quasar absorption lines and their relationship to galaxies. After that, he moved on to a postdoctoral fellowship at the Institute for Advanced Study in Princeton, and then became a senior research associate at the Canadian Institute for Theoretical Astrophysics in Toronto. Then he spent a year at the Kavli Institute in Tokyo, where he is still on the faculty. And he joined the faculty at the Johns Hopkins University in 2010, where he has continued his groundbreaking work on the distribution of cool gas and dust around galaxies, most of which has taken advantage of very large public data sets using very innovative statistical techniques to mine these data sets. In 2012, the Maryland Academy of Sciences awarded Brice, or judged Brice the Outstanding Young Scientist of the Year in the state. And in 2013, he was awarded the Sloan Fellowship. So, prepare to be impressed.
Thank you, Kate. And thank you, everybody, for the invitation. I'm going to tell you today about how to basically try to map out the large-scale distribution of baryons around galaxies. Feel free to interrupt me anytime during the talk. Do not wait for the end if you have any questions. So most of the work I'm going to present today has been done in collaboration with Guangtung Chu, who is a postdoc working with me at Johns Hopkins University. So here is the context. When we look at the sky, this is an image in the optical, we see photons that are basically emitted by stars. But as you might know, only 6% of the baryons are in stars, and the question is, what about all the rest? Okay. Where is it located? Is it in this dark space which is between galaxies? What is its spatial distribution, its properties, etc., etc.? Those are some of the questions we are going to address. And these questions originated to a great extent by some work that was done in the 90s. This is a cosmic baryon budget by Fukugita, Hogan, and Peebles. And so what these people did back then is to try to come up with an inventory of all the known sources of matter in the universe. So this is basically where the whole missing baryon problem originated from. This was in the 90s. There was a major update of this work in 2004 by Fukugita and Peebles. This is now the cosmic energy inventory. So before it was only about mass, now it's about energy. So this is much more general. This is a fantastic paper that I recommend everyone to read. So these authors go through all the known sources of energy in the universe and estimate their contribution to the total budget. It's a very nice paper. It is also a very hard paper to read. This is something like 30 to 40 pages without a single figure. So it is quite dense. But you are very lucky today because just for you, I have turned this entire paper into one figure, which is here. So this is basically a visualization of this cosmic energy inventory. The y-axis that is here is the only relevant one. Shows cosmic density in units of the critical density. Okay, so all the quantities here are presented in a way that is unitless, and we can see the relative contributions by dark energy, dark matter, baryonic matter. So the x-axis here does not carry any meaning. This is just a way to open the tree and visualize what's going on. And one of the big questions here, if we focus on baryonic matter, for example, is to understand different constituents are distributed, how do they interact with each other, etc. We can learn a lot by looking at this figure. I have learned a lot. we can notice, for example, a very nice property. If we look at the output of stars, okay, so this is now average over cosmic volume. So stars basically produce 3 kinds of output: photons, neutrinos, and dust. And just something for you to remember, if you look at it here, okay, if we look at photons produced by stars, so this is the cosmic density of stellar photons, the cosmic density of stellar neutrinos, and the cosmic density of dust, and they are about the same. Okay, this is very nice. Keep in mind that this is 10 orders of magnitude in this scale. All right, so let's try to have a closer look at these components. So here the whole game is very similar to what has happened in the weak lensing field over the past 15 years or so. The question is, can we come up with tools to basically probe this dark space between galaxies and characterize the distribution of matter, gas or matter in the solid phase, which is dust grains? If we're interested in gas, we have a very handy tool at our hand. We can use absorption line spectroscopy. So this is an example showing the transmission of some simplistic type of ISM gas as a function of wavelengths. So if we are blueward of the Lyman limit for this kind of hydrogen column density, it's opaque. Then we find the Lyman series, Lyman alpha, and we have all sorts of absorption lines that are just illustrated here. And so one of the goals here, so we can use quasars, for example, to detect these absorption lines. And one of the goals is to understand the relationships between this gas traced by these absorption lines and galaxies. Okay, so what people have been doing in this field for many years is to look for correlations between absorber systems and galaxies. Okay, we understand galaxies much better than we do understand absorbers. So if we can measure a correlation between the two, then this is going to provide us with some guidance to understand the physics of these absorbers and this distribution of gas. But to do so in practice, it's extremely hard. People have been doing this for a long time. I'm going to give you a quick historical summary of what has happened in this field. It started all the way back in '69 with Baryons and Spitzer. Back then, they didn't have any pair of galaxies and absorbers. That was, by the way, here's their abstract. This is the full abstract of their paper. But this was a great postulate. They observed the incidence of metal absorbers that they detected in quasar spectra. And they say that if those absorbers, so back then they had absolutely no idea of what they were, but if those absorbers are related to bright galaxies, they basically say that then it means that bright galaxies must be surrounded by a huge halo of gas, extending all the way to about 200 kiloparsecs to be able to reproduce the incidence of these metal absorption lines that they observed. And they were basically right. And since then, we have learned more about this gas distribution, but it turns out that it's not that much more. So historically, so this was just postulated. It took many years. We are at '69. It took many years. We have to wait all the way to '86 to have the first detection of a match between an absorber system and a galaxy. So we have a redshift in emission, a redshift in absorption. The two systems are separated by about 60 kiloparsecs. Okay, so the gas is probing the dark matter halo of that galaxy. And it is in '86, with some work done by Jacqueline Bergeron, that we have the first demonstration that this postulate by Baryons and Spitzer was correct. So that was great. Many people started to work on this. Around '95, Chuck Steidel and collaborators came up with a compilation of about 50 galaxy absorber pairs. Okay, so this is nice because we can now start to look for trends and statistical results. So this is an illustration of one of their results. This is an HST image. There is a quasar at the center, and this is showing part of the spectrum of this quasar. And what is important to note here is that one of the results that came out of this is that all the galaxies with a white label in this image, this one, this one, this one, this one, they are all detected in absorption in the line of sight going towards this quasar. So this means that it is very likely that there is a very large distribution of gas around this galaxy that extends at least all the way to this radius. Okay? And what Steidl and collaborators showed back then is that this is a very common property of galaxies. So their result was basically up to about 50 kiloparsecs. It's very common for galaxies to have cool gas around, giving rise to these strong metal absorption lines. That was also very, very nice, and we learned a lot from that. But then, so here we have about 50 galaxy absorber pairs. I would like to mention the fact that it is very difficult to do this kind of work, because so it is easy to take the spectrum of a quasar and detect absorption lines. But then to figure out which of the galaxies in these fields are connected to these absorbers, this is very expensive. One needs to take spectra of many of the galaxies in the field and look for matches. And we will have a huge contamination due to foreground and background galaxies. So it will take a lot of time and a lot of telescope time to be able to come up with this identification and these 50 pairs. During the next decade, many people, for example, Chris Churchill, so Steidl basically came up with the spatial distribution. There is this cool gas all the way to about 50 kpc, but not much more than that. And during the next decade, many people tried to look for correlations between absorber properties and galaxy properties. And we saw a number of papers like this one where we can see this is the rest equivalent width of magnesium to absorbers, and the authors are trying to correlate that with a number of properties that they can measure for the galaxies, but this has led to null results. Okay, it has been very difficult to measure any correlation. So a number of people played this game. A few years ago, there has been a very nice result coming out of the COS Halos team. So far, people had focused at low redshift on these metal absorbers to study these galaxy absorber connections. But recently, we got UV spectroscopy again on HST, and that has allowed people to focus in this part of the spectrum and to look at higher ionization species. And for the first time, after many years of study, this is the result obtained by the COS Halos team. This is a paper by Jason Temlinson. They have found a very nice correlation between the properties of the gas. So what is shown here is the column density of oxygen 6, which is measured in the halo. Okay, we are talking about scales of about 200 kiloparsecs here, and the specific star formation rate of the galaxy that is at the center of this halo. Okay, so for the first time after 15 years of attempts of measuring correlations, by looking at high ionization species, people have been able to basically find a correlation. And as you can see, so there is a big difference between the gas halos in oxygen 6 for star-forming galaxies and passively evolving galaxies. So this is very interesting. At the same time, people have continued to try to look for correlations with low ionization species. So some of these people extended their observational campaign to get about 200 absorber galaxy pairs, and they tried absolutely any possible correlation that they could think of with galaxies. And the result of this is that there is no correlation between some of the properties of the cool gas in the halo and galaxies. Okay. So this is what can be done with targeted observations. Now I'm going to show you what can be done if we approach this problem in the context of large surveys, and I'm going to use Sloan. So the idea is that we do observe all these absorption lines with a survey like Sloan, and we are in a regime where we have access to about 200,000 quasars. So what can we do with that? So having so much data is great because it's an opportunity, but at the same time, it's a real challenge to be able to detect all this absorption line in a coherent way for so many objects. So this is now starting to show you what we have been doing at Hopkins for the past 2 years. So we took quasar spectra in Sloan. Quasar spectra have some nice properties if we want to detect absorption lines. And the whole challenge here is to be able to come up with this red line. Okay, so the black data points show a real spectra from Sloan, and the red line is an estimate of the quasar continuum. If we want to detect these absorption lines automatically for hundreds of thousands of spectra, and especially if we want to detect very, very weak absorbers, we have to be able to come up with an estimate of the continuum in a very robust and automatic way. The challenge is the following. There's a whole diversity of quasar spectra. They have different luminosities. We can normalize for that, but then they have different slopes. We can normalize for that, but then we find that they have all sorts of possible shapes for their emission lines, etc. In addition, we have other effects that are in the way. We have to deal with sky emission lines, galactic absorption, and the absorbers that we are interested in. We actually did all of this at Hopkins. This is Guangdong Zhu, who has done a lot of this work. We came up with a data-driven way to estimate the continuum of these quasars. And at the end of the day, we have an algorithm that is fully automatic, that doesn't have any free parameter, and that is able to find this red line for all quasars in SDSS in a very robust way. It can deal with sky emission lines, quasar emission lines with all their varieties, low signal to noise, even missing data, and it's not affected so much by intervening absorbers. So how did we do that? As I said, this is a data-driven estimation of the continuum. So first I'm going to tell you about one technique that is being used a lot with large data sets, which is principal component analysis. Okay? So here the idea is that if we have a large collection of objects, in this case, for example, human faces, what we can do is to treat each of them, so this is one, don't think of it as a 2D image, but just think of it. So this image has n pixels by n pixels, so we are working in an n square dimensional space, and this image is just one point in this space. Okay? And so we can look, if we have many faces, we can look at the distribution of points in this multidimensional space. And PCA is going to tell us basically what are the axes that carry most of the variance, okay, of an entire population. And by being able to characterize those axes, we can reduce the dimensionality of the problem, we can simplify it, and we can use the eigenvectors that we find as a model to reproduce faces. So what is shown here are the eigenvectors, or the eigenimages, if you want, coming out of such a decomposition. The first one is the mean, okay, of many faces, and then we see the first departure from it, the second order, etc., etc. When it is black, it is positive. When it is red, it is negative. Okay? And what we can do is that we can just take a face, project it onto that basis, we find the eigencoefficients, and we can reconstruct this face by simply taking the product of these eigenvectors by eigencoefficients. This is all great, this is very standard, and this is not what we have used. What we have used is actually a new technique which was which basically is coming from recent developments in statistics. This problem was solved in '99. So the idea here is that we want to do a similar vector decomposition, but we want everything to be non-negative. And we as physicists really like this because we work with energy, with photons, so we don't want a decomposition to give us negative values. So this has an extra constraint, which is the non-negativity of the decomposition. And it has a number of very interesting properties. So we can play a very similar game. And as you can notice here, all the red has gone. All the negative values that PCA has have disappeared. The decomposition is different. And the vectors here are no longer orthonormal. But that's not a problem. And as you can see, we can come up with a whole series of positive coefficients. And if we just take the product, we can recover our face in the same way. Many of the properties of these vectors are quite interesting. As you can see, this is a sparse decomposition. Most of the pixels are white. They are basically zero. The pixels that are set to a non-zero value, they tend to be all together. Okay, so this is very good at basically extracting parts of an object. And I do not have time to discuss this, but this is also how our own brain works. The neurons we have in the brain, they fire either 0 or 1. They don't do -1. Okay. Another property is that if you look at the PCA decomposition, you see that so you can recognize a face. But very quickly, as you go to higher orders, you do not see any face anymore. But in this case, you can recognize parts of faces, eyes, nose, mouth, etc., etc. So the decomposition is qualitatively different. We have applied this to our quasar spectra, and this is what's coming out. I'm just showing you. So we take all the quasar spectra in Sloan, we apply this decomposition, and we find the equivalent of eigenvectors. And this is what's coming out of it. So that decomposition does not know anything about physics. But if you look at some of the first eigenvectors that come out of this, you find broad emission lines from quasars, you find some continuum, you find forbidden lines all together in one vector, you find hydrogen lines in another vector. This is a very nice and useful decomposition. Once we have these vectors, we can use them to estimate the continuum of all the quasars. And those are some examples. The red line here is the continuum estimate. Same thing here. We are not very much affected by the sky emission lines. So now I'm going to apply this to the entire Sloan data set.
Question.
Yes. not so much. I can come back to that in a bit. I mean, there will be just a few pixels out of the entire spectrum, so their weight is going to be negligible at the end. Let's have a look at the whole Sloan data set. This is now, as a function of quasar redshift, this is all the quasar spectra in Sloan, showing you that, as we go to higher redshift, we are seeing shorter wavelengths, and that gives you an idea of what we end up detecting. I'm going to turn this now into an image, which is shown here. So we have the observed wavelengths. We have quasar redshift here. When it's bright, it means that there is more emission. You can see that quasars are blue. You can find all the emission lines. Pay attention to the fact that this is not a regular axis. We simply put all the spectra on top of each other. So that's why these lines are not straight lines. Okay, they bend, and this reflects the redshift distribution of the data set. Now we can use our new technology. We have this very nice piece of algorithm that allows us to remove the continuum and look at residuals. So we are going to apply this to the entire image, and this is what we get. So orange here is the continuum level. Okay, this is 1. And when it is white, it's emission above the continuum, and black, it's absorption. You can see the Lyman alpha forest over there. What we are seeing here, by the way, we are seeing only like percent level residuals. This is very, very flat. It works really well. You can notice also all sorts of features. There is this very bright line here, okay, which is at 1 wavelength in the observer frame, and this is oxygen emission from the atmosphere. You can see the OH emission lines as well. And this is also showing you that the Sloan pipeline does not fully subtract those lines. This is after sky subtraction, and what we can see is that on average, the Sloan pipeline under-subtracts those lines. Okay, so we could improve things. Something that you cannot see here is the presence of all these absorber systems. So we have thousands and thousands of little black dots in this image. You cannot see them here because this is very low resolution. This is made out of 100,000 quasars, so I would need many, many screens in order to show that at full resolution. But believe me, they are there. We can detect them, we can measure their redshifts, and then we can study them. So to show you that they are there, I'm going to basically show you those black pixels that we find, and I'm going to enlarge them so you can visually see where they are. So this is an example of magnesium-2 absorbers. So magnesium-2 is one of the strongest absorption lines. That's why so many people study and love magnesium-2. It's very easy to detect. And so we do detect these magnesium-2 absorbers. They are in front of the quasar, so they are blue shifted compared to the quasar magnesium-2. And this is where they all live. Here we have a gap because we do not try to detect them when we are on top of the carbon-4 emission line, because things get a bit more difficult. Okay, so that was just artificially enlarging them. Now what I'm going to do for you is the following. I'm going to take this data set, and without doing anything special, so you know that we can detect all these black dots, I'm going to reorder this image. Instead of using quasar redshift, I'm going to use absorber redshift. Okay? So what's going to happen here is that all these little black dots that are there but you cannot see, as a function of absorber redshift, they are going to fall next to each other. All right? And this is how it looks. All right? This is just the same image, just rearranged as a function of absorber redshift. Okay? So now we are going from redshift 0.5 to 2 point something. The strong magnesium-2 absorbers, all these black dots that I enlarged for you, they basically now fall along this line. This is the magnesium-2 doublet. And you can see a whole series of absorption lines as a function of redshift. And this is based out of about 50,000 magnesium-2 absorbers that we have detected in the Sloan quasar spectra. So this is basically the visualization of this catalog. The catalog is publicly available. Feel free to download it and use it. It can be used for all sorts of studies. Many things can be seen here, so we can see all sorts of weaker lines. We can see something that is also interesting. There is a weak track here. This is calcium-2 absorption. Okay. If we extrapolate this all the way to redshift 0, we would fall somewhere around here. All right, at around 39 something. And if you pay attention in this image at that wavelength, you have 2 vertical bands here. Okay, can you see it? This is calcium-2 absorption due to our own galaxy. Okay, so if we look at quasars, all the lines of sight have to go through our own galaxy, and we are seeing calcium-2. This is showing them a bit better here, the 2 vertical bands that are here. This is calcium-2. the dark line that is here is sodium D absorption due to the galaxy. Plotted in this way, it's not very interesting because this axis is quasi-redshift, so those two do not correlate at all. But if we look at these two lines as a function of galactic latitude, for example, we see that as we go down the plane, their amplitude increases. So we can actually use all these quasi-spectra in Sloan to come up with a mapping of calcium and sodium absorption in the sky. And we get maps like this. I just have a side question for the students and the postdocs in the room. This calcium 2 absorption is also called calcium H and K. Do you know why it is called calcium H and K? I have noticed you do not know why. I can also ask the question to the faculty, apparently. Okay, very interesting. Exactly. So this goes back to Fraunhofer, and I'm mentioning this for several reasons. Okay, this is Fraunhofer, who is one of the first people who looked at the spectrum of the sun. This is coming from his own publication. This is the figure in the publication, which was drawn by hand. This is from 1814. This is exactly 200 years ago. This is the birth of spectroscopy. Okay. And as you can see from his own paper, he simply, from the red to the blue, he simply wrote the letters A, B, C, D, etc. He used capital letters for the stronger lines. Okay, and this is where calcium H and K come from, and sodium D come from. The D has nothing to do with atomic physics.
I and J out to lunch. Between H and K.
In this nomenclature I's here, there is no K. It took me 1 month to understand where K came from. And I had to talk to some historians. K did not come from Fraunhofer. Fraunhofer was actually interested in measuring refraction angles to estimate the indices of refraction of different materials. So he was actually using the lines just as reference points to measure angle differences. And in his case, he was not very much interested in the second line because the spacing here is too close. So he actually only focused on one, and the K nomenclature came about 60 years later in the literature. All right. I'm glad you have learned something. So this is the visualization of this catalog. We have 50,000 absorbers. It's all on the web. It's going to be updated soon to the new Sloan data releases. It's going to go up, and it's going to be about 70,000 systems. So what can we do with them now? Okay, so let's start to play. So first we can, so when we measure an absorption line, we can measure its strength, or its equivalent width. If we look at this magnesium 2 absorbers, okay, people have done that for a long time. If we simply plot the distribution of equivalent width, so this is the equivalent width here, okay, just the strength of the line, and the number, we find that there is a beautiful exponential distribution. This is exponential, there is an exponential cutoff here, and there is a parallel tail here. So this is Schechter-like. Okay. At this point, nobody really understands why this is the case. Okay. The day when we will fully understand this distribution, we will have learned something fundamental about these absorber systems. We can look at how this evolves with redshift, and this is something we can do very well with our data set because we have so many absorbers. I'm not going to go to the details here, but I'm just going to show you this plot. If we look at the strong magnesium 2 absorbers and we plot their incidence as a function of redshift, okay, this is what we find. So this is what's coming out of our own analysis from SDSS. And this is an extension which is coming from near-infrared spectroscopy done by Rob Simko and his group at MIT. And as you can see, so we are spanning a huge redshift range, and this looks very familiar to many of us. And if I overplot the Madao diagram, this is star formation rate density as a function of time, they are very, very similar. And so this is extremely interesting because the points here, the blue and green points, okay, so this is telling us about the incidence of absorbers. So this is gas that is living in the halo of galaxies, 50 kpc, 100 kpc away from the galaxy. And those are absorption measurements. And the gray points, they are showing us emission measurements from the galaxies themselves, okay, the star-forming regions. So we have two very different scales here, but on cosmological time scales, they seem to track each other. So there is something very important here. We have to understand this physics better now. But there is definitely a link between that gas on 50 kpc scales and the star-forming activity of galaxies. So this is something that we can actually address as well with our large catalog. we can also play the same game and try to look for correlations between absorbers and galaxies. And there's something very interesting here, and something, an aspect about a general aspect of big data analysis. When we have a lot of data, it's not that we can do things more precisely, it's that we can do things differently. And in this case, I told you how difficult it was for people to study these connections to find absorber-galaxy pairs, because one needs to go after the galaxies, follow up, get the redshift, and find matches. When we have so many objects, we don't even need redshifts anymore. Okay, and I'm going to show you how we can do that. What we can do is to take quasars with absorbers. We put an aperture around them, and we count how many galaxies we find. We do not care about the redshift of these galaxies. Then we do the same for quasars without absorbers. Okay, and what we will pick here are just the overall distribution of galaxies as a function of redshift. Okay, and if we have many of those systems, we can just statistically look at the difference between the two. And that difference will automatically pick up the galaxies that are connected to the magnesium-2 absorbers we are studying. So we can now do that without any galaxy redshifts. Okay? By construction, this correlation will pick the galaxies at the redshift of the absorbers. The rest is just background, and it's being removed by doing this operation. So we have done that with a number of surveys. We can cross-correlate our absorbers in Sloan with galaxies in Sloan in galaxy in WISE. I'm going to focus on what we have learned from Sloan in this talk. This is now work done by a graduate student at Hopkins, Ting-Wen Lan. So this is what he has found. So he has done this experiment just sitting on an absorber and counting how many galaxies we find in different surveys. So you can focus on the green points for now. So this is the number of galaxies that are found in excess. Okay, so this is above the background as a function of redshift. And in Sloan, so we can detect this magnesium-2 absorbers from about redshift 0.4. And as you can see, in the Sloan images, we can find many pairs. Okay, so 70% of the magnesium-2 absorbers at redshift around 0.5, okay, they have a galaxy in the Sloan images. Okay, those are very fine galaxies. Redshift 0.5 is kind of pushing it for Sloan, but we can find these objects. And because we see this tail, we can even say that in the Sloan data set, there are galaxies going all the way to about redshift 1. Not that many, of course, but they are there. Otherwise, there wouldn't be such a correlation. We can do the same with WISE and GALEX and study the relationships between the two. So what I'm going to show you now, I'm going to focus only on the low redshift range where we have this very high detection rate. And let's see what we can do. So historically, I showed you that this is by how much the samples have increased. And with our techniques, statistically, we can come up with a sample of about 2,000 absorber galaxy pairs. An order of magnitude increase. And very nicely, when we reach that regime, finally, after so many years, we start to see the correlations we were looking for. So to give you a flavor, this is what some of the things we can see. What is plotted here, so because we have so many galaxies, okay, about 2,000, it's very easy to break them into different bins of magnitudes or different strengths for the absorbers, etc. So this is basically what this diagram shows. So if we look at the top, we are focusing on small-scale surround galaxies. And we can see that absorber systems are surrounded by both blue and red galaxies. Okay, what the x-axis here is G minus I, it's the color of the galaxy. Okay, so we see this bimodal distribution. And as we pick stronger and stronger absorbers, we see that the population of blue galaxies increases. Okay. Now, if we start from these strong absorbers on small scales and we go to larger scales, we see that there is an inversion. On large scales, we have more red galaxies than blue galaxies. So finally, we can start to study these correlations. Plotted in a different way, if we look at what's going on small scales, this is the number of galaxies as a function of the strength of the absorption. So what we find is that if we pick these magnesium-2 absorbers, there is an excess of red galaxies around them, but that excess is not at all a function of equivalent width. Okay. However, if we look at the blue galaxies, the stronger the absorber, the more likely it is to have a blue galaxy within 50 kpc. And we can extract some interesting information from that slope. I'm going to now convert this into physical quantities, which is what you will care about much more. What is shown here now is, out of this entire sample, what is the excess absorption as a function of galaxy properties. Okay, and what we see is that there is a threshold above which, in star formation, for example, above which suddenly the absorption will start to get stronger. Same thing as a function of stellar mass, but the trend is seen only for the blue galaxies, not for the red galaxies. And this is specific star formation. So finally, we now can detect these correlations, and this is basically the first step towards understanding the physics of what's going on between gas in galaxy halos and the properties of the galaxies themselves. So just to summarize at this stage what we have learned, just by using this large sample, we can look at the distribution of rest equivalent width. It is like a Schechter function. Why? We don't know yet. The redshift distribution looks very similar to the cosmic star formation history. And now we can start to basically measure the scaling relations between absorber properties and galaxy properties. There's one missing ingredient here if you really want to start to study the physics. It's to know something about the spatial distribution of the gas. I haven't said anything, not much about it so far. So this is something that we have addressed, again using Sloan, but from a completely different angle. Let's start again. This is showing the quasars in Sloan. We have about 200,000 of them. As you know, we can very easily get rid of their own emission and just look at the residuals. Okay. So now let's think of this a minute. In the first part of this talk, we have made use of all these little tiny dots that we can detect directly, all these absorption lines. Okay? But now let's think about it more broadly. There are many absorbers in this map, or many absorption lines that are too weak to be detected directly, but they are there. They are just below the noise. Okay? So we can think of this as actually a map of flux fluctuation in the sky. So we measure it at the location of all the quasars. So we have a map of flux fluctuation, and we have this information as a function of wavelengths. Okay, and you should think of it as a field which has some noise. Okay, so at the pixel level, this is completely dominated by noise. Most of the time, we do not detect any absorption, but we know that there must be absorption almost everywhere at a very weak level. The good point is that we have many, many pixels. Okay, we have about 600 million pixels, so we can do statistics with that. So there is absorption, which is below the noise, and we know that this absorption is correlated with the presence of galaxies. So we can extract that signal by doing a cross correlation between this flux fluctuation and the 3D position of galaxies. All right? This is exactly the same operation as saying I'm sitting on a galaxy, and I'm going to stack all the absorption signal coming from background quasars in the vicinity. Okay? So let's do that. We take our absorption field and we take a galaxy sample. For example, low redshift galaxies from Sloan. We know that if we work at this redshift, we can pick the calcium-2 H and K absorption. So by simply doing this cross correlation, we can do this as a function of scale, of separation from the galaxy. This is what we get. So what is shown here, they are basically mean spectra. As a function of impact parameter, this is 7 kpc, 20, and we go all the way to about 200 kiloparsecs. And this is the mean absorption that is seen as a function of impact parameter from galaxies. So with this technique, we are able to measure flux fluctuations down to the 10 to the minus 3 level. This is very, very similar to what people do with galaxy-galaxy lensing. They measure shape distortion statistically, and here we measure flux decrements. So this is the calcium-2 doublet that is detected. And if I turn this into a radial profile, what I'm showing here now is the equivalent width of calcium, the strength of calcium absorption, as a function of scale. And this is going all the way to about 200 kiloparsecs. So here we are really probing the dark matter halo scale of those galaxies. And calcium-2 had not been detected frequently beyond 20 kiloparsecs around galaxies previously. And here we are really extending this probe. We can now learn something from the amplitude and the scale, and to give you just a flavor of what we can do, we can break this as a function of galaxy properties. So what is shown here, we can decompose our galaxies as a function of stellar mass, high stellar mass, low stellar mass, and we see how the gaseous halo reacts on the stellar mass of the galaxy. This is as a function of star formation rate. Blue galaxies have much more gas around them. And this is an attempt to see if we can detect a dependence on azimuthal angle. And there is a hint that there is more gas perpendicular to the disk of galaxies in this case. Okay, so we can study all of this, and basically this is taking us much closer to the physics of what's going on. But we can do even better than that. So calcium 2, if you remember from this orange image, that was one of the weak lines. Okay, we can apply the same technique to some of the stronger lines, for example, the magnesium 2 lines. Okay, so let's go back to our estimator. We want to cross-correlate an absorption map and a galaxy sample. This time I'm going to use luminous red galaxies at redshift 0.5. So this allows me to look for magnesium 2 absorption. Magnesium is not detectable in the optical at redshift 0.1 in the previous case, but at redshift 0.5 we do see those lines. So if I measure this, this is what's coming out of it. Okay, so this is the mean spectrum. As a function of scale, this is 40 kpc, and this is about 10 megaparsecs now. Okay, and as you can see, we detect the magnesium 2 doublet. We even detect magnesium 1 on small scales, and we can measure its strength as a function of scale. We are now pushing the analysis all the way to a 10 to the minus 4 flux fluctuation. So from the Sloan quasar spectra, we are actually able to measure absorption at the 10 to the minus 4 level, 1 photon out of 10,000. This is very nice. So if we put this in this figure, this is absorption strength as a function of scale. Okay. So what you see here is the absorption profile, the mean absorption profile around galaxies. Okay. On small scales, it's going to be dominated by the galaxies, by the luminous red galaxies we have chosen, and on large scales, we have the contribution coming from all the neighboring galaxies and the large gas structure. To put this in perspective with what was done before, those are the measurements that exist in the literature of other lines studied in a similar way. The yellow points come from the latest study of Bordeloy. The pink ones come from Chuck Steidel, who has studied cool gas around Lyman break galaxies. And the blue ones are the points I just showed you previously. This is our calcium 2 profile around galaxies. So now by focusing on magnesium 2, we can really push this exploration to a new regime, because we can go beyond the viral radius of galaxies. Yes?
What effect does the variations in metallicity and ionization state play in this? You're looking at a given absorption feature, which can vary, for no other reason, by the metallicity in that area.
Absolutely. So there are extra steps if we want to go from this observable all the way to estimating the total amount of magnesium, or even H1 if you want. Yes, there are assumptions. I'm not going to go in this direction yet, but I'm going to show you a bit more. That might help. So now what I'm going to do here, so this is now showing the surface density of magnesium as a function of scale, and I'm going to try to use a model to explain this. And what I'm going to do is to use a very simple assumption. I'm going to say that gas follows dark matter. And if that's the case, I can use the so-called halo model to describe the statistical properties of this distribution. And so what the halo model tells us is that we can decompose a density profile as two components. There is a one halo term on small scales, which is the density distribution coming from the galaxies we are looking at. This is an NFW profile, okay? And it is scaled with some gas to mass ratio. And on large scales, this is now given by the statistical properties of dark matter halos. We have the two halo regime. Okay, and it is only scaled by another gas to mass ratio. So I only need three numbers to describe these two profiles. One is the mass of the luminous red galaxies, which is basically going to set this scale. And then we have two amplitudes on small scales and on large scales for the gas to mass ratio. If I take the sum of these two components, I get the blue line, which is a very good representation of what we are observing. So at the end, I only need three numbers to basically explain this entire distribution. So let's look at the value of the values of these numbers. So what is shown here, on the y-axis, this is the magnesium 2 gas to dark matter ratio. And this is the mass, the halo mass of the luminous red galaxies. Okay? And by simply using this halo model, I can extract those parameters from the measurement. And what I find is that the best mass for the LRGs, just using the gas distribution, is about 10 to the 13 point something. And on this axis, I can read the magnesium to mass ratio. And as you can see, if we use the value measured on small scales in green and on large scales in yellow, they are about the same, which might even say that there are only two numbers that describe the entire system. to compare this with what people have done, so this region shows the estimated mass of luminous red galaxies coming either from galaxy-galaxy lensing results or galaxy correlations. As you can see, there's a pretty good agreement. Now let's try to have a closer look at this number. This is what's coming out of this halo model, so it is a bit model dependent. Let's try to get away from that. What we can do is to come up with a gas to mass ratio which is completely model independent. So on the left we have our result, which is the gas profile around galaxies, around luminous red galaxies. And on the right I'm going to use measured data points from galaxy-galaxy lensing results. This is work done by Rachel Mandelbaum. It is not exactly the same redshift. Okay, so soon Rachel will basically come up with similar results at that redshift. We will be able to use exactly the same galaxies to compare those two. But if we neglect for a moment the evolution between those two different redshifts, we can just take a ratio between the two. And so this is the gas, the magnesium to gas to dark matter ratio as a function of scale. What is very impressive is that over 3 orders of magnitude in scale, this is very flat. All right, and this is model independent. We are taking 2 sets of observables and just taking the ratio between the two. Now, if we look at this value, okay, that is coming from this model independent estimation, this is where it lands. So this is telling us that the halo model is doing a very good job at describing the distribution of gas, the mean distribution of gas around these luminous red galaxies. All right. So now let's come back to our measurement. Okay, so those are showing the mean absorption spectra as a function of scale. And again, we are able to probe a range of absorption from 1% to about 10 to the minus 4. So far I have talked about the strengths of these lines, but there is more information here. As you can see, on small scales we can resolve the magnesium 2 doublets, but on large scales we cannot. The lines get blended. All right, so we can extract this information, and this information is telling us about the velocity dispersion of the gas. And if I plot this now as a function of scale, this is how it looks. So this axis is the line of sight velocity dispersion of the gas. Okay, so basically the width of that doublet as a function of scale. Again, it's measured all the way to 20 megaparsecs. Okay. I can use again now my halo model, okay, to describe this distribution. This is now the halo model in velocity space. This is what comes out of it. So we have set the mass of the luminous red galaxies. So that completely defines the 2 halo term. Okay, this is just dark matter statistics. This is what's coming out of the 2 halos. So this is the velocity dispersion of galaxies around the luminous red galaxy. Okay, so this is a halo-halo velocity dispersion type of quantity. And on very large scales, we are picking up the Hubble flow. All right, so this is what is given us, for example, by dark matter simulations. And it seems to be in good agreement with what we measure. So this is indicating that here we are measuring gas that is sitting in other halos and is orbiting around the luminous red galaxies we are considering. And what about small scales? This is what is predicted for the velocity dispersion of dark matter in the 1 halo regime. Okay? So this is much more than what we are seeing when we look at these magnesium 2 clouds. This is actually expected because these magnesium 2 clouds, when they are within the halo of a luminous red galaxy, they cannot move freely. They are going to feel the pressure of the hot gas that is in the halo. Okay, and this is not the case for the dark matter particles. So this is expected. Okay, and if we want to describe this distribution, we need to introduce what is called a velocity bias. So we need to suppress the amplitude of this 1 halo term here. It's about a factor 2 or 3. And now if I take the sum of these 2 distributions, this is what I get. And what is beautiful here is that the blue curve here needs only 1 free parameter. The rest is fully described. And that 1 free parameter is by how much I need to reduce the velocity dispersion within the dark matter halo. Okay. So this is telling us about, basically, again, it's putting us much closer to the physics of what's going on. And what we are going to do next is to now try to come up with simple models to be able to explain this. And what is this factor 2 to 3 that we find in that reduction. Okay, I'm going to now show you one more cute result, since I have enough time. So far I have used quasars as background sources, but we should not limit ourselves to quasars. We have many, many galaxies from this Sloan Digital Sky survey, so let's try to use them. So similarly to what I showed before, this is now the distribution of spectra for galaxies, for luminous red galaxies. So the redshift range here goes from 0.15 to 0.6. Okay, and what you can see here is that luminous red galaxies do not evolve with time. Okay, the spectra are very stable. So we can basically play the same game. We can remove the continuum of all these galaxies. Okay, we get the 0 point. It is much harder in the case of luminous red galaxies because there are many more wiggles. So as you can see, this is noisier than what we got for the quasars. But in this case, we have about 3 billion pixels. Okay, so it is even more than what we had with quasars. So we can play the same game. We can cross-correlate this absorption field with a distribution of galaxies. Okay, and this is what I'm going to show you now is just a preliminary result. We have not finished this analysis, but what I'm going to do is the same as before. I sit on low redshift galaxies from Sloan, and I look for calcium-2 absorption, not in background quasars, but this time in background galaxies. And we have only processed 10% or even less of the full data set, and I just wanted to show you that we are starting to see this absorption signal in the same way, using galaxies instead of using quasars. So this is very nice because it opens up a whole avenue of new studies of gas in the universe. All right, so to try to basically summarize several of the points that I've made during this presentation, during the first part of the talk, I've basically taken the classical approach of absorption line studies. So we have a field of absorption in the universe, and we have some floor which is given by the noise level of individual spectra. And by doing so, we can only study the strong absorbers which are above the noise level. Okay? And in the context of Sloan, we could come up with a catalog of about 50,000 such systems, which was great because now we know that this is enough to start seeing correlations between gas in the halo and galaxy properties. But in addition to that, we have also in the second part of this presentation taken a statistical approach. And here we are basically digging below the noise. And by doing so, we cannot see the individual features. What we can do is to probe the moments of the full distribution. Okay, this is exactly what is done when people do correlation functions. But the advantage is that we can go below the noise by orders of magnitude. As I showed, we can now measure flux fluctuation in Sloan spectra at the 10 to the minus 4 level statistically. So it allows us to go very deep here and get a sense of the moments of its distribution. And the analogy for people who do lensing is the same as doing strong lensing and weak lensing. Okay? With strong lensing, as shown here, we have these giant arcs. We can see them by eye. Here we are in the signal-dominated regime. We don't need any statistics to detect the gravitational lensing signal, but we are limited to study only the very inner parts, the high-density regions of the matter distribution. If we use weak lensing, okay, we now apply the statistical approach, we are no longer limited to these regions. We can actually apply these estimators to the entire sky. And so this is now what we are starting to do with spectroscopy. Okay, and it's very interesting because we are no longer limited to the tip of the iceberg, but we can probe the full distribution. In the future, there is fantastic potential for these studies because we have a number of upcoming surveys which are going to provide us with many more millions of spectra. So the main point is that we have now already some of these absorption maps. The only thing we need to continue doing these studies are new galaxy redshifts. And by using galaxies at different redshifts, we can access different species, different absorption lines. And so there is so much more to learn from these maps and so much more signal to extract. And this is something that we will be able to do in the near future with all these surveys. All right. I'm now going to summarize all of this. So what we did is to take the Sloan survey. We were able to come up with a very nice algorithm that can estimate the continuum of quasars using some modern statistical techniques. And thanks to this, we were able to detect 50,000 absorbers from Sloan. Again, this is fully publicly available. That can be used for all sorts of studies. When we play with this kind of large samples, we can now have access to all sorts of new possible measurements. For example, we can study absorber-galaxy correlations without knowing anything about the redshift of the galaxies. This is a great advantage. As I showed also, by simply looking at the incidence of systems as a function of redshift, what we find is that this gas surrounding galaxies on scales of 50 to 100 kpc knows something about the overall star formation history in the universe. So this was all in a signal-dominated regime. And what I showed during the second part is how to use statistics to go below the noise and to extract some extremely useful information on the spatial distribution of gas around galaxies. What I showed you here is an example using luminous red galaxies, but this can be done around any type of galaxies. And in the future, for example, using SDSS-4, we will be able to do this around star-forming galaxies at redshift 0.6, 0.7. I have shown you what is actually the galaxy gas correlation function, measured over a broad range of scales from the 1 halo regime, where we are dominated by the galaxies. We are looking at all the way to the 2 halo regime, where the signal is coming from neighboring galaxies. And this was measured both as a function of both for the strength of the absorption and its velocity properties. Now, if we try to think of this in an even more global picture, we have now reached, after about 10 years or 15 years of SDSS, at a point where we have a collection of such measurements. So you all know the galaxy-galaxy correlation function that has been measured for several decades. And with these surveys, we have also been able, for example, thanks to lensing studies, to look at the galaxy mass correlation function. This is measured all the way to megaparsec scales again. We have been able to study also the distribution of dust around galaxies. This is the galaxy dust correlation function, also detected on scales of megaparsecs. And now that we have developed all these tools, we can start to basically come up with a whole new series of measurements giving us the distribution of gas around galaxies. And so I think this is now going to be a new starting point to study galaxy evolution in a statistical context, not only looking at the galaxies themselves, but also taking into account this information coming from the 2 halo regime and neighboring galaxies. Thank you.
You just showed the magnesium 2 halo mass.
Yes.
Ratio. If you were to put in some type of a gas for magnesium, what would be the gas to dark matter?
The gas to dark matter ratio. So if we, on small scales, we can measure the H1 column density. So this is now trying to combine together different data sets, different redshifts, so it's a little bit dangerous. But on a scale of about 50 kpc around an L-star galaxy, the H1 column density for this kind of magnesium 2 absorbers is about 10 to the 18.5 centimeter minus 2. So then that can give you the scaling for this profile. Not yet.
All right.
Once we come up with mass estimates, which those are some of the next steps, definitely, then yes, we can go back to the cosmic energy inventory in this diagram. We can try to estimate how much mass we have on large scales and what is the contribution. But what is often found by doing this exercise, which is difficult because there are ionization corrections and so on, but there is basically a similar amount of baryons in the halo as is in the disk. So that's what seems to come out of this calculations. Yes?
Do you have constraints on the cross-section for the correlation on the bottom right? So in other words, if you look through a galaxy, do you always find a weak absorption line, or is it a combination of strong lines in some cases?
Yeah, so we do have this. I do not have it in the slides. I can show you later, and it will be published quite soon because the paper is almost ready. From the study, using the 50,000 absorbers that we have, we can actually measure the cross-section. What is the probability to hit an absorber from a galaxy? So this is measured, and we have the profile all the way to hundreds of kiloparsecs, or megaparsec scales even. So if you're interested in this quantity, I can give it to you. Yes?
If you separate field galaxies versus cluster galaxies, do you see any significant differences?
We will. No, we have not done all these things yet. We have spent the past 2 years developing all the tools to be able to make these measurements, and this is really, for example, for this one, this is taking all LRGs and seeing what we get. The next steps for the next few years is going to look at different types of galaxies, orientations, environments, etc. I think this is going to follow a very similar path as galaxy-galaxy lensing. 15 years ago, people just got a global signal around all galaxies, and then there has been a whole industry of measuring this as a function of galaxy properties. We can do the same now with this. Now the tools are in place. Just give us a little bit more time, or join us if you like.
How does the metallicity, can you say something about how the metallicity changes with redshift or with radius, just based on simple ionization corrections and the ratios of lines that you're seeing?
As a function of scale, that would need many assumptions about ionization corrections and so on. People from the COS Halo team who have access to UV spectroscopy, they can do that. So they are limited to a sample of 50 galaxies. But so they have a direct estimate of the amount of hydrogen, and they are now looking at some of the metal lines. So they are starting to be able to combine, to gather enough information to address this question. So this is coming up here.
Well, what about as a function of redshift? I mean, at least you could use magnesium to iron 2 or something like that.
We have not done that yet. But if you are interested, the magnesium 2 catalog is public. It comes also with iron 2 and other line measurements. Feel free to download it and use it. We have been limited just by time. There is so much to do with all of this. Yes.
Do you know yet if the pressure you require in the hot gas is compatible with the warm hot intergalactic medium prediction?
I do not know yet. Again, I'm presenting results.
Yeah.
This is all new. That was this is all very recent. We have not yet pushed to the next level. But yes.
Are there any perspectives of using those background galaxies, as you shown in the last part of the talk, with sodium deabsorption, which is much stronger than calcium, presumably at low redshifts?
Absolutely. Yes, this is doable. Yes.
Is there any significant advantage to having more quasars? Like, for example, EBOS is going to get a lot more quasars between redshift 1 and, say, 2.5 that's limited.
Yeah, so there are, if you have more quasars, you can increase your signal to noise because you have better sampling. But what you can start to do if you have more quasars, you can sit on quasars, and you can use this technique with background quasars to probe the gas distribution around quasars, and that will be quite interesting. So I think the main improvement with SDSS-4 is to have, on one hand, more quasars, and we will also have many spectra of these blue galaxies at high redshift. So we can actually now extend these measurements not only around red galaxies, but we can look at blue galaxies, star-forming galaxies as well. I think that's going to be quite interesting.
Did you want to speculate on the redshift distribution plot that you showed us of the number of absorbers and the star formation rate? Did you have an idea for what might be the connection between those two things?
I do. So I believe that these magnesium 2 absorbers that we see, they are basically due to outflowing gas around galaxies. We have not yet been able to demonstrate it. It turns out to be very difficult because the problem is very symmetric. It's difficult to argue that it is not in falling gas that is fueling star formation. That's the difficulty. But hopefully at some point we will be able to come up with a very good argument. I didn't show it, but in this analysis done by Tim Wan Lan, we are able to look at the distribution of gas as a function of azimuthal angle. And what we find is that the excess is perpendicular to the plane, which is a very strong indication that this is outflowing material. And we see that only around blue galaxies. Around red galaxies, the distribution is isotropic. So that is one argument towards the outflow scenario, and I think this is why the two quantities are linked as a function of cost of time. Yes.
Question on that. So the absorbers, though, in the Gauss plot that you those aren't the same systems that are shown in this.
No, so in these figures there is not a single detected absorber.
Okay, so
all the information is coming, it's below the noise if we look at individual spectra. Yes, so This is basically what people used to throw. Okay, they would detect an absorber, just a few pixels, and ignore the rest, and this is just using the rest. And this is extremely interesting.
So looking at your nice image here, it looks like you have a very nice measurement of the mean flat field error in Sloan spectra. Are you taking that out? I mean, it seems like when you're probing down these very small levels, you want to...
Oh yeah, so when we are probing these small quantities, we actually mask all this excess emission here. Yes.
I'm trying to work out whether this is even a sensible question. You've been showing the mean residuals. Do you gain anything from looking at the variance about that mean?
Yes. So when I said earlier that what this does is to probe the moments of the distribution. Okay, so when we are in this regime, so the analysis that I showed today was basically to look at the mean absorption level of the entire distribution. Okay, and if we look at the variance, then we will probe the second order moment of the distribution. So we can push that and extract more information.
Okay, let us thank Brice again.